SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we started to talk about frequency spectrum, and this frequency spectrum becomes a very important concept, especially in turbulent flows, because we are talking about a wide range of length scales. Why is that? In laminar flow you only have a single length scale, whereas in turbulent flows you have a wide range of length scales. So because of that, every length scale is associated with its own frequency. So frequency analysis becomes important. A spectral analysis becomes important. And as a starter, we look at the frequency spectrum here. So we already looked at the autocovariance. Autocovariance came into play because when we thought about a turbulent flow, when we discussed a turbulent flow, we realized that a one-time CDF or a one-time PDF cannot alone characterize a turbulent flow, because there are things that happen over a period of time, and there is a relationship between what happens at one particular point in time and another point in time, because the flow behaves in a random manner. So that meant that we would need to consider a joint PDF or a joint CDF where you consider multiple times. Now, to make our life easy, in order to simplify the system, what we did was, let's consider a statistically stationary process, which means all the statistics are stationary with respect to time, as in they are constant with respect to time. One such statistic is the autocovariance. The autocovariance is the mean of ut times ut of t plus s. That means you are taking the variance of the velocity of one component of velocity at one particular point in space at one point in time with respect to another point in time, that where s is the lag time or the lead time. So that would be equal to the variance times the autocorrelation function. This is by definition. Now this autocovariance and the frequency spectrum form a Fourier transform pair. We already saw that last class, which means the frequency spectrum is the Fourier transform of the autocovariance as shown here, and the autocovariance is the inverse Fourier transform of the frequency spectrum as shown in the second equation here. So because of the fact that your autocovariance is an even function, because it is an even function and you have e to the minus I omega s given by cosine omega s plus I sine omega s, your equation turns out to be r of s cosine omega s from 0 to infinity. So all you need to do is, because you have an even function multiplied by an odd function, you could the odd function goes out to be 0 if you have a symmetric integral. So minus infinity to infinity, you can write it as 2 times 0 to infinity. That's the reason why you have cosine omega s. We already saw that. And then the autocovariance can be written as the inverse Fourier transform of the frequency spectrum. So that is e omega times my I omega s. Again, by the same reasoning that an odd function will turn out to be, if you integrate it over a symmetric plane, it will turn out to be 0. So we need to consider only the even functions, which is why you're considering e omega times cosine omega s. Remember, cosine is an even function, sine is an odd function. So that is where we stopped, isn't it? Where you had the autocovariance and the frequency spectrum forming a Fourier transform pair. Now, what does that leave us with? So the idea is, if you consider omega, if you consider r of 0, so you substitute s is equal to 0 in the previous equation here. If you put s is equal to 0 here, then r of 0 becomes 0 to infinity E of omega, and because S is equal to 0, cosine of that 0 becomes 1. So it is E of omega d omega. Okay, great, and that is what you're getting here. So R of 0, by definition, R of 0 would be from here. R of 0 is U of t squared. So the squared is inside the angle bracket. U of t squared multiplied by rho of 0, which is 1. So this comes out to be U of t squared average. So that's the variance. That is essentially what we are getting here. R of 0 is U of t squared, which is integral of 0 to infinity E of omega d omega. Now, obviously this is mathematically true, but what is the physical significance? Think about it. Your integral of the frequency spectrum over the entire range of frequencies is this one here, right? This is the integral of the frequency spectrum over the entire range of frequencies. That integral gives you the variance of the velocity, of the fluctuation of the velocity, I should say. So that is the physical significance, that is one of the physical significances of the frequency spectrum. So if you have a frequency spectrum that looks like this, E of omega and versus omega, and if you integrate it over a range, if you integrate it over the entire range, you will get the variance. If you integrate it over a particular range, say omega A to omega B, then you will get the contribution to the variance due to frequencies in that range. That is what we mean. So E of omega d omega from omega A to omega B is the contribution to the variance of all modes in the frequency range. So that is the physical significance of the frequency spectrum. So this is why looking at a frequency spectrum becomes important. One, you have these length scales where you have varying ranges of length scales, and each length scale is associated with its own frequency. So a frequency analysis is important. You would have to look at a frequency spectrum. And in addition, if you integrate the frequency spectrum, what you're getting is essentially the variance. So that takes us to the integral time scale. Now, we already looked at how we defined the integral time scale earlier. So I'm going to go back a few slides and show the definition of the integral time scale. As you can see here, it is the integral of the autocorrelation function. That is your integral time scale over the entire range, 0 to infinity rho of s ds. And that, so you're integrating with respect to that lag, isn't it? When you take the covariance, the autocovariance, you're taking the variance of velocity with respect to time, and where s is a lag. So depending on whether s is small or large, you could have a wide range of s. Now we already saw earlier that as you get s keeps increasing, then your autocorrelation function diminishes, and that's the reason why this particular integral shown on the slide converges, and so you get a finite value for the integral time scale. We already discussed that. So that s is the lag. So this is the definition of the integral time scale. Now coming back to a further relationship of the integral time scale, you can have a connection between the spectrum and the autocorrelation, where you have the time scale which is pi e to the 0 divided by 2 u squared, as in variance. So how do we get that? So I want to show how we get that. So we have our frequency spectrum as e of omega 2 over pi 0 to infinity r of s cosine omega s ds. Now this is it was initially, by definition, it was minus infinity to infinity, but because sine is an odd function, that goes out to be 0, and you're left with this. Now if I substitute omega is 0, then what I get is e of 0 is 2 over pi 0 to infinity R of S ds, isn't it? Because cosine of 0 goes to 1. So this is what you have. And then by the definition of the autocovariance, you can write this as 0 to infinity u squared variance and rho of S ds. Now this is a constant, so this will come out of the integral. So you would have 2 over pi u squared integral 0 to infinity rho of S ds, which is by definition the integral time scale. So that is 2 over pi u variance times the integral time scale. So from here the integral time scale is pi e of 0 divided by 2 variance. This is how we get that equation. So this is the relationship between the integral time scale and the frequency spectrum E of 0. Obviously variance is in there. Now let's relate this with this knowledge. Let's relate this to the 5 random processes that we had seen earlier in the previous class. So I'm going to go back, just to refresh your memory, I'm going to go back to those 5 random processes shown here. Remember, just to reiterate, the first one is a measured turbulent velocity. The second one is a measured turbulent velocity except at a higher frequency. So possibly, just for your understanding, it is probably at a higher Reynolds number. That's how you get it at a higher frequency. C is like a Gaussian process, so that has nothing to do with a turbulent flow. D is an Austin-Olympic process, which is a stochastic process. Again, nothing to do with a turbulent flow. And E is a jump process with the same spectrum as that of D. Again, nothing to do with a turbulent flow. So only A and B are associated with a turbulent flow. All of these have the same one-time PDF. They have the same one-time PDF. And however, there are some similarities between some of them. For example, A and B are different frequencies, so let's keep that aside. C, a Gaussian process, has the same spectrum as that of A. Okay, and D, the stochastic process, is the same integral time scale as that of A. And E, a jump process with the same spectrum as that of D. Okay, with that, let's go to now the spectrum. Okay, so if I go here, the high frequency process B has a smaller integral time scale than that of process A. Why? Because it is at a higher frequency. If it is at a higher frequency, you would expect it to have a smaller time scale. Naturally, it would have a smaller time scale. And if it has a smaller time scale, that means it would have a smaller value of E of 0. So B, which is a higher frequency process, will have a smaller time scale. If it has a smaller time scale, it will have a smaller E0. Let's see if that is the case. If I look at A and B here, so this is A and this is B. So look at B. B has a smaller E0 value. This right here is this is for A, E0, and this is B, E0. As you can see, the B E0 is less than A E0. That is expected because B is at a higher frequency. So because it is at a lower time scale, so because it is at a higher frequency, it has a smaller integral time scale and hence a smaller value of the frequency spectrum at the lowest frequency. A smaller value of the frequency spectrum at the lowest frequency. This will all have significance when we start to look at turbulent flow. But for now, just understand this. Now, the other thing is the autocorrelation function of the spectrum is usually the only quantity used to characterize multi-time properties. That is the only quantity. But as we already know, the one-time PDF and the autocorrelation function only provide a partial characterization, isn't it? Because this is all we have. We need a multi-time statistic in order to look at, in order to fully characterize the system. This autocorrelation function or a one-time PDF only partially characterizes the system. The other point I want to make with respect to this figure is D and E are qualitatively quite different. We already saw that. However, they have the same one-time PDF. And because they have the same one-time PDF, they have the same autocorrelation function. And because they have the same autocorrelation function, they have the same frequency spectrum, as you can see here. Both D and E have the same frequency spectrum. However, if you actually look at what the plots look like, look at this, D and E, they couldn't be any different. They look vastly different. However, the E has the same spectrum as that of D, and that is what you're seeing in the frequency spectrum. When I plot the frequency spectrum here, D and E have the same spectrum. So the conclusion is that a one-time PDF and an autocorrelation function only partially characterize the system. They do not completely characterize the system. We looked at all of these quantities. Yes, D and E are very similar here, but as you know from the signal, they are vastly different. That is the conclusion from this analysis here. Now, let's take a side step and look at a statistically stationary Gaussian process. So we already know what a statistically stationary process is. It means the statistics do not vary with time. Now let's take a Gaussian process. Why are we considering that? It is important to understand the differences between an actual turbulent flow and a Gaussian process. Now, at the outset, if you record a velocity at a single point in space, a component of a velocity at a single point in space, and if you plot it, it might look visually very similar to a Gaussian process. And I'll illustrate that through some figures. However, they are very different. Okay, so let's think about this. If a process is Gaussian, then the general n-time PDF is joint normal. So a normal distribution means a Gaussian distribution. So if you take an n-time PDF of a Gaussian distribution, it is going to be joint normal. And that is a standard distribution. And again, like I was saying earlier, you need a joint multi-time statistic, isn't it? A joint PDF in order to completely characterize the system. So we are trying to see if we can do that. So the distribution is fully characterized by its mean and its covariances. And for a statistically stationary process, the statistics do not vary with time. So UT-UN, this is like the variance, and this is actually the covariance, right? This is the autocovariance, I'm sorry. So UTN and UTM is the autocovariance, which is UT squared variance times the autocorrelation function. So instead of writing it in terms of S, which is the lag, we are writing in terms of the difference between two times, which is exactly what the lag is. Now, if you have a statistically stationary Gaussian process, then the mean stays steady. So it can be completely characterized by mean, variance, and the autocorrelation function. Because this is a standard process, you are able to completely characterize everything here. Now, earlier we saw what a Gaussian process looked like, right? So, for example, again, going back to those 5 random processes, this was the Gaussian one. This was the Gaussian process. Here, this has the same spectrum as that of A, as in a turbulent flow. However, it is still Gaussian. Now, like I said, A and C at the outset looks kind of similar. You could mistake one for the other, but they couldn't be any different. And that is clear by doing some deeper analysis. That's what we are delving into right now. So if I go further and think about it, the statistically stationary Gaussian process is completely characterized by its mean, variance, and autocorrelation function. Now, process C is defined to be a Gaussian process with the same spectrum as that of A. This is what I was saying, but there are some differences. For example, if I take the double derivative, okay, the second derivative, u double dot t is d squared u over dt squared. Now, if you look at the Gaussian process, it follows that u double dot t is also Gaussian. So what is shown here is, so as much as u of t and for A and C, for the process A and C looked similar on paper, if you take a second derivative, you can see that they are very, very different. The top one is for the turbulent flow, and this one is for a Gaussian. Now it is clear, the difference is very clear. So the second derivative is Gaussian. And so the kurtosis of u double dot, which is like the higher order moment of the second derivative, is 3. Whereas in a turbulent velocity process, the process A, u double dot is far from Gaussian. So if for a Gaussian process, if you take the second derivative is also Gaussian, and for a Gaussian process, the kurtosis is 3. It's a standard value. Whereas for a turbulent velocity field, the second derivative is anything but Gaussian, and the kurtosis in this particular case happens to be 11 when you calculate it. So they are very different. So we are trying to make this point just to show how a turbulent velocity field is very different from a Gaussian field. And so we should not be under the assumption that just because the signal on those 5 random paths looked the same between A and C, looked similar between A and C, doesn't mean they are the same. So do not try to mistake a Gaussian process for a turbulent. Do not try to approximate a turbulent velocity field with a Gaussian process. They might look like that on the outside. They might look similar on the outside. But as you can see from this very simple experiment, I would say, where you take the second derivative, the Gaussian process is very different from a turbulent velocity field. So now that we have looked at frequency spectrum, I think it is now time to look at random fields in terms of velocity vectors. So we made life a lot simpler by just looking at a single variable. So we always looked at a single component in velocity. In fact, we were just looking at one velocity, one variable. But as we know, we are dealing with the turbulent flow behavior. Turbulent flow is 3D. There are 3 components, and it depends on the 3-dimensional space. It obviously depends on time, but it depends on a 3D. So what we have is a random vector field. So now on the slide, we will use bold letters to indicate that it is a vector. But when I write it, I will use vectors on top of it to indicate that it is a vector. And now when we consider the velocity vector, we have to consider this PDF of the velocity vector. So for each component, you would have a CDF. For each component, you would have a PDF. And that it would still be one time because we are not considering at multiple times. And it would be at one point because we are measuring each component at a single point in space. So in that sense, it is one point and it is one time. So it doesn't consider multiple times. So we have now f of v. Your sample space is also now a vector. So v of x, again vector, comma t is the probability of ui, a single component of velocity, being less than equal to vi, where I goes from 1 to 3 for x, y and z. Then you have the joint PDF, which is defined as the derivative of your CDF, but because it is a vector, it is now a triple derivative. It is now a third order derivative. So your f of v, indicating that v is a vector, x comma t, x is again a position vector, it is del cube f del v1 del v2 del v3 of v comma x comma t. So at each point and time, this PDF fully characterizes the random velocity vector. But again, it contains no joint information for 2 or more times or positions. So here this is only for a single point in space and single point in time, not for multiple points in space or multiple times. So just so that you are clear with the notation, in terms of the PDF, the mean velocity field, that is the semicolon notation, indicates that f is a probability density function. because you are taking it with respect to V1, V2, V3. Okay, with respect to the sample space variable. That is what we are doing. So what we'll do in the next class is we will now look at averages based on this. Now that we have defined the random field, we will consider averages based on this, variances based, just like we did for the random variable. Then we will go into frequency spectrum for the 3D random field, the covariance for the 3D random field, now that we have understood those concepts. So what we have done in today's class is we looked at the covariance in the frequency spectrum. We tried to understand the physical significance of the frequency spectrum, how it is related to the variance, how it is related to the time scale. And we looked at the frequency spectrum in the context of those 5 random process paths that we had seen earlier, and looked at how the frequency spectrum was different for some of the cases that we had shown. Although for D and E, for example, they were identical, and they were meant to be identical because D and E had the same spectrum. Then we looked at time scale of those fields. That took us to now extending all of this into 3D, because everything that we have been looking at so far included only 1D, a single variable. Now we are looking at a 3D random field, and that's what we are going to do in the next class. Thank you.